So this thing's kind of, is this thing like an online thing? I brought a bunch of stickers. I don't know if anybody wants these stickers.
Yeah, that's cool.
Yeah, people like stickers? All right. Cool.
Around area.
And could somebody go into the YouTube to make sure we are online and you can hear the sound? Yeah, I can see myself, and I do not know we can hear the voice. Yeah, this voice is coming from my another YouTube video. Is it? Yep. Yeah, sounds good. All right, so I just queuing this one. All right, so everything looks cool. All right, let's start. So thanks for everybody to coming on the public holiday in Japan. I'm very sorry that I didn't realize it's a public holiday today. I just set up and some people asked me, is it really having the meetup today or not? And just wondering why so many people start asking me the question. I just realized like last week it's public holiday, but I didn't find any other spots. So anyway, so here we are. So it's how many times right now? 48? It is, yep, it's Tokyo.net Developer Meetup 48. And even though we have less people in the room and we have a bit more people online because of the public holiday, the great news here is we have two people coming from the Redmond, the product team. One from Cosmos DB, so we cover the database side, and another from the function. So we are covering the front end side, right? We only need somebody to talk about the Blazor so that we can cover the entire picture. Anyway, anyhow. All right, so before starting, there is some announcement I need to make for our own sake. So as you may or may not know, we have the Ignite coming right in 2 weeks. Do you know where the Ignite is this time? Atlanta? Orlando. So Orlando Ignite will be like the November 4th to 8th, something like that, right? The first week of the November. Then after that, we have the Ignite tour. So we going all over the world to just giving more the sessions for people who cannot come into Orlando. So one of the sessions will be held in Tokyo, which is December 5th to 6th. And the good news is it's free. You just register, you just come, no charge. And if you live in the west side of the Japan, no worries. We still covering you guys because we also have the Ignite tour in Osaka, yay! And obviously we have less people in Osaka registered yet. So if you have any friend, the partner, and somebody else living near this area, please encourage them to go in. I don't really mind if they come into Tokyo. I'm very welcome and very pleased to have them in Tokyo, but please announce we also have the event in Osaka as well so that the people living the west side can take advantage of this one. All right, so that's a quick announcement. And Mark, do you want to present something, by the way? You don't have to decide right now because we still have time later. So like if you can give us a quick overview, what is Cosmos DB kind of stuff might be interesting. And by the way, everything go online. And if we find something inappropriate, we can delete it later.
I can talk kind of quickly about kind of overview of Cosmos, or I can do, I don't know, how much time you want to give me?
All right, so up to you, like from 5 minutes to 30 minutes. And because this is .NET Developer Meetup, not so many people are familiar with the NoSQL kind of type yet.
Yeah, I can
So,
talk, I can do like a 20 minutes on Cosmos.
Cool. And if you have a slide deck, just send me via Teams so that I can provision.
I got decks and demos.
Yeah. And decks and demo or decks or demo, it's up to you.
It's both.
Okay, cool. All right. And now we need Katy, but I don't see her in the room. So, but I don't want to waste our time. So let's start from my session first then. All right. So today, the original plan was I just being the only one speaker explaining about the .NET Conf. So how many people knowing about .NET Conf? Nobody? Never hear? this is a shortened way of the .NET Developer Conference kind of stuff, right? But the .NET Conf is the official name of the event. And let me try to find my slide here. All right, so today, the reason why I want to have the .NET Developer Meetup today is give motivation to watch .NET Conf video. By the way, each video having like 20 to 60 minutes, and they have 77 videos. So it's quite enough to killing your boring time. So I think I recommend you to watch during your commute or anything else. But Katy! I saw her face. Never mind. All right. So .NET Conf is a conference for the .NET developer, and this is a virtual event, meaning I think they have some physical event as well, but I think this is more like a virtual event, so that everything online, everything on the YouTube and channel 9, and the people will participate online. And we also have the .NET Conf in Tokyo this weekend, and I think we already did in Fukuoka. So this is more like a community-driven event for .NET.
A drink.
Yeah, of course, yeah. So the first thing first, what is .NET Conf? So if you go into this https .NET always this .NET something .NET is confusing me. But the .NET Conf.net is a place you can find what it's all about. But now we have Katy back. So Katy, do you want to give your presentation first?
Yes, sure.
Yeah, before you go for a sleep.
Yes.
All right. Before going further, let's change the gear a bit, and I just pass in the speaker to the Katy so that she will present about the durable function.
Hi.
Hi. Right. Let me switch to your slide then. And I just need to go back.
Okay.
All right. And you have a hand mic if you want.
And also.
Yeah, of course I can do that. Yeah,
USB.
sure. So I hope it's connected right now. Could you try to just do? No? There you go. All right. It's up to you.
さあ始めましょう。
Yay.
Okay. I've been talking in Japanese, or to the best of my ability, pretty much all day. So let me switch gears back into English.
Yeah.
So hello, my name is Katy Shimizu, as Ken-san said. I am a software engineer out of Redmond at Microsoft. I work on the Azure Functions team. I've been there for about 2 years, had my 2-year anniversary in September. And I've worked on, the kind of one of the big things that I've done is JavaScript support for durable functions. And I've recently shifted over more to working on support for the core Azure Functions runtime. And if you don't know any of these technologies that I just mentioned, don't worry, you will. Yes, I have a Twitter and I have an email. It's amazing. All right, so let's talk a little bit about serverless first. How many of you are familiar with serverless, or both hands up if anybody is using it and building things with it at work? Okay. So just Pierre there. No. Oh, you too. Okay. Cameron too. All right. Okay, cool. So we'll start with just kind of an overview of what I like to think of as the case for serverless, and kind of why serverless is, what the advantages of it are, and why people want serverless. So in the bad old days, as it were, there's my laser pointer. So in the bad old days, which I'm actually a little bit too young to remember, as I understand it, you had to maintain your own servers. You had to either rent space from a data center, or you had your own data center. You had a legion of systems engineers, and you had to be concerned with, your scaling. You had to have your scaling operations. You had to write your own scaling logic that might have been very manual, you had to worry about patching and upgrades and configuration and all of the stuff that goes kind of into the care and keeping of server racks. And that's actually kind of it's a lot of overhead. If you're a software company, or if you're a company that, well, these days every company is a software company, but if you're a company that uses software for something, you really want to focus more on your business logic. You want to focus on the stuff that is your domain-specific knowledge, as it were, and not babysit a bunch of these machines. So this is kind of where cloud providers first came in. They said, okay, we'll manage the machines for you, and you can remote in. You can configure things for you, but we will handle the actual hardware. And that's kind of the definition of IaaS, or infrastructure as a service. And people were like, okay, I'm okay with giving up this level of control in return for not having to think about my hardware so much. And also, not going into the data centers because it's freaking cold in there. So kind of the next step along the way was PaaS, or platform as a service. And so in PaaS, you have those servers managed by a cloud provider, but then we add a layer of software or framework on top of that. I think someone mentioned that they work with Azure App Service. Yes, no, maybe so? Okay. So App Service is an example of a PaaS offering. And the whole idea behind App Service is it's this software layer for hosting websites. And there's a lot of configuration and management, and we provide an environment for creating and hosting websites. And there's some scaling rules in there and so on, but there's still some stuff you have to think about there. Namely, like, let's say I'm hosting a website. Let's say I've got an e-commerce site, and it's Christmas time, or it's Golden Week is more for vacation. So let's say it's Christmas time, and suddenly, my traffic, which has been pretty steady, spikes because everybody wants to go and buy Christmas presents. I need to make sure that I have the instances to handle that. And even though my hardware is being managed by my cloud provider, and the whole website management experience is, kind of also built there for me, I need to think about how many instances of this website that I want. And I need to think about when they're going to scale. So manual scaling means, someone has to be twiddling the knobs to say, okay, give me 3 instances, back down to 2. And honestly, sometimes traffic is very bursty. Sometimes you have a pattern that you can't really predict when you're going to get a large influx of traffic. I mean, maybe your site made the front page on Reddit, and that's why you're suddenly getting all of these visitors. But either way, you can kind of see some of the disadvantages, or some of the overhead that's still there with PaaS. So the next step is serverless. And despite the name serverless, there are servers. One of my colleagues, Jeff Holland, who you can probably see him at .NET Conf and Ignite, he likes to explain the term as you think about your servers less. This is totally a justification for a very bad term. But that's basically the idea. So in serverless, all you really need to worry about is your code. So we manage kind of your application execution environment for you. You upload your code, and then we're managing server updates, we're managing hardware, just like with PaaS. But we're also managing more than that. We're managing your scaling. So if you think about, so when people are like, okay, what's serverless in a nutshell? I kind of look to these 3 points. The first thing is that your servers are abstracted away from you. You don't need to think about your infrastructure at all, pretty much. And your scaling is kind of auto-scaled. So Within Azure, if you were running on a serverless hosting plan, we have a component called the scale controller. And what the scale controller does is it watches the kinds of events that are triggering your functions. And like, say, for example, if you have a function that runs every time you get a message on a queue, maybe you're doing some sort of processing on that queue message. Well, the scale controller will monitor metrics like your queue's depth. And if it notices that the queue is getting too deep, it'll go, hey, okay, I need another instance. The other thing you can do is if there's nothing in your queue, it's like, I don't need any of these instances, and it can giveth and it can taketh away. So in a scenario where you don't have any function invocations being requested, your application under the serverless model may not be provisioned anywhere on Azure. It may not be living on any VMs. Whereas in an app service or a PaaS kind of environment, you still have to, you're like, well, I just want it for this day and that day. You don't know when you're going to need it, and there's nothing really monitoring it to say, okay, I know you're kind of up and down. So instead, you're buying your plan in like monthly chunks, and regardless of the kind of usage, you're still paying, your monthly fee. It's like I don't know, it's like renting an apartment and not really knowing when you might be there to use it. Whereas serverless, you can think of it more like maybe like a hotel room or an Airbnb, just as you need it kind of thing. So that also kind of leads me to my point about the programming model. So with you can think of it like a kind of an ephemeral kind of application, in that sometimes it's only there when it's needed, right? Well, how do I know when I need it or not? And the answer to that is events. So with serverless, you have a shift to a more event-driven programming model. So you're looking at an event coming in, triggers some code does something, maybe writes to some output, boom, we're done. And that allows you to scale based on your event metrics. And because of this scaling, because sometimes you're not provisioned on any machines at all, and because there's monitoring around that, that means that your pricing model changes. So under serverless, instead of the I rent an apartment kind of scenario where, yeah, I pay for the month, and regardless of whether I use it or not, that's what I pay. Instead, we have micro-billing. So these are usually per-use transactions, or based on the based on the amount of compute you're using up, or kind of a mix of the two. And I think on the functions consumption plan, you get I think it's like 1 million free executions or something. They're very cheap to run. And if you have no traffic at all, well, you're not paying for anything because you're not using any of the space or the compute on our machines. Basic idea. So I've kind of touched on a lot of the benefits of serverless that come out of this model. One of them is kind of your productivity. So you can just focus on your business logic. You're not worried so much about the ops component. It's not like I have to have my systems engineers who go down to the data center every month and walk along the racks. I have to have people watching for security vulnerabilities and patching to the latest OS and so on, because your cloud provider takes care of that for you. And I was speaking at Serverless Tokyo earlier today, or Serverless Days Tokyo earlier today, and there I told a story about kind of the first time it was not long after I joined Microsoft, and it kind of illustrated to me the kind of maintenance and the kind of work that your cloud provider is doing on your behalf for your infrastructure. So this was late 2017. I had been there maybe like a month or two, and there was a very official-looking email in my inbox from someone maybe 3-4 levels of management above me, and it was sent to the entire organization that I'm part of. So not just my little team, but the greater encompassing team. And basically it said, hey, so yeah, there are these security vulnerabilities that some researchers have discovered. They're kind of serious. They kind of affect pretty much all the CPUs known to, pretty much like a majority of CPUs. They're chip flaws or firmware flaws. And yeah, that includes our machines that we run Azure on. So this is bad. And we need to pivot, and we have a patch. We need to roll that patch out across all of our workers and our machines. And that's, when you think about a cloud provider like Azure, that's hundreds of thousands of machines. This is not a small undertaking. So it was getting close to Christmas, and we had other work that, we had other priorities, but this just kind of came in and interrupted everything. So as a team, we kind of pivoted, and all our attention went to getting this patch out across our workers as quickly as possible, without downtime for our customers, so that, yeah, they'd be safe. And we did it. We did it. Kudos were had. And then on January 2nd in 2018, I'm looking at the news app on my phone, and I see an article that Google security researchers have revealed some serious vulnerabilities in nearly all CPU chips. And if you've heard of Spectre and Meltdown, yeah, that's them. So we had already gone through and fixed it on all these machines. Our customers didn't have to worry. Okay, so that's one of the nice things, right? Another is, like I said, you're really only doing your code plus a little environment configuration, so you can focus on your business logic more so than, okay, time to visit the server racks. And that means that you've got a faster time to market. So with serverless, because you're just kind of focusing on your code, you can spin up prototypes. You can throw them up really quickly. You're not having to set up all this boilerplate. You can just be like, okay, here's my code, plug it in here and here. Let's try something. You can, you can do a prototype in an afternoon, tear it down, make it into something more substantial, whatever you want. So I'm kind of talking about this from the perspective of functions because I'm on the functions team. So I'm naturally my mind is a little skewed in that direction. But the serverless application platform on Azure actually consists of several components, and not all of them are listed here, but these are some of the critical ones. So functions, that's that little bit of code that you upload and then it runs in response to a trigger, does some output kind of thing. We'll talk a little bit about that model as we move into durable. And then there's also something called logic apps. This is a low to no code kind of visual-based workflow that allows integration with various third-party services. So you can kind of just make like a flow chart of like when I receive a tweet with this and run through sentiment analysis and do this and this and this and this and this. So some people kind of like going that way. And then there's also Event Grid, which is it's sort of a big pub sub network capable of handling many events, and it acts kind of as a nexus point that other services connect off of to trigger like the next step in whatever your serverless application is doing. And then there's also some other stuff. So like database, Cosmos DB now has a serverless offering, I think, right, Mark?
Yeah, almost.
Almost, okay, almost. We're still in preview?
Not even really announced yet, actually.
Oops.
So,
okay.
Thanks for that.
Can we bleep me out?
Yeah.
Okay. But yeah, so these kind of serverless components interact with a bunch of other existing Azure components. So storage, we have security and access control. I think this is AAD. This is probably like blob storage. This is IoT Hub. This is stream analytics, so for running analytics on streaming data. And this is a brain with circuits, and my mind is blanking on what that means. But that's our ML AI. Cortana, yes, thank you. Thank you, the thing that I turn off on my laptop. Okay, right. And then the other part is your development environment. So we provide IDE support for a number of different IDEs you want to use to develop serverless in. We provide integration with DevOps, including so like the Azure DevOps platform, GitHub Actions. If any of you have tried those out, that's something that we're doing integration with. We provide local development experience monitoring. There's a lot of integration with application insights. And if you are able to catch the Ignite announcements, I know we're going to be talking about Azure Monitor, which is currently in preview. And then a visual debug history. I am not entirely sure what this is. Maybe it refers to remote debugging. Anyway. So I've been talking about FAS. FAS is kind of at the center of serverless. We've kind of talked about some of the principles of FAS. I've alluded to them. So event-driven and scalable, right? We've kind of gone over that one. They are short-lived. So you're not meant to have if you're writing a function that just that's around for, a very long period of time. Maybe it's running some extremely intensive work. Maybe it's acting like an infinite loop to monitor something that's not really in the spirit of serverless. I mean, we get people trying to do that, but maybe there's a better approach, or something a little bit less, a little bit less hacky. And the short-lived kind of goes hand in hand with single responsibility. So these functions they're small pieces of code that do like maybe they're like a function in a traditional code base, right? They've got kind of one thing that they do, or that's the idea. And the other part of that is that they are stateless. So all the function really knows about is in a single execution. Okay, here's the data that I triggered off of. It's not aware of any other function executions that happened before it or after or in conjunction. It just runs off what it's got, does some stuff, it can call external APIs or whatever, and then goes into output. That's the programming model. So these two parts, first time I learned about serverless, I'm like, yeah, okay, that makes sense, that's cool. But there are some complications that come from that, because a lot of the workflows or a lot of the business processes that you work with, they're not short-lived and they're not stateless. So how do you translate that to a serverless environment and take advantage of the benefits of serverless without doing something terrible to your architecture? We'll talk about that. Anyway, I think I can skip over this slide. I've kind of talked about the programming model for functions, events, code, outputs, boom, boom, boom. All right. So these are some of the sample scenarios that you can have for functions. These are places where, these are situations when functions and sort of a serverless approach might fit really well. So file processing, if you're wanting to resize an image, I think is our classic example. IoT connected backends, that's a lot of data coming in from your IoT devices. You can process it, do stuff with it in functions. Conversational bot processing. And you can also write APIs, so REST APIs and other kinds of backends. And automation. So if you have something, just a little short job, it's like a cron job. If you just want to run a little bit of code on a scheduled basis. We have a timer trigger that you can use to run on a schedule and do whatever, and then it just shuts down when you're not using it. Okay, so another thing with functions is that because we are open source, we can run, you can take you can clone the repo on GitHub. You can build it and you can deploy it wherever you want. We also provide support for a number of hosting scenarios. One that I really like is when I'm in development, running on my local dev machine. I can run the whole functions runtime just on my machine. and test my invocations locally. And make sure that I don't have to deploy to a staging site, run my tests there, tear it back down if something doesn't work, develop and kind of function blind that way. I can do a lot of it on my dev box. And then once you're moving into staging and prod, we have a couple of hosting plan options. So I've talked a little bit about the consumption plan. That's the pure serverless hosting plan. You spin up and spin down as needed. You're billed on a per execution basis. The Azure Function Service, this is more the dedicated plan. This is the rented apartment kind of scenario. It's not a serverless plan. It predates serverless, but we do find customers sometimes run functions on that plan, maybe because they like the functions programming model or for other reasons, but maybe they're doing some really intensive processing work. And in the consumption plan, we actually impose a 10-minute maximum execution time on any one function invocation, and then we kill your process if it's gone past that. So sometimes stuff takes longer than that in some of these applications. So those customers tend to go to the app service plan to run stuff from within there. And then this is new, and we're actually going to be announcing GA of it at Ignite. So watch there for specific dates. But the premium plan is sort of a hybrid between the consumption plan and the app service plan. So let's see, how do I put it? So the idea of serverless is that, yeah, I have a request come in, I spin up an instance if I have none running, and I run, and then I spin down. Well, there's a term in the serverless world that refers to the delay when you have 0 instances of your application, and that request comes in, or your queue message comes in, and the time it takes, the lag time between going from 0 to 1 instance, is called cold start. Because it does take time to provision a machine, to load the code on there, to configure the environment, and we do try to do as much of that upfront as possible, but there's still a bit of lag. And cold start is kind of the bugaboo of serverless. And if you're running something like let's say an API, where the occasional latency of a couple of seconds, isn't really acceptable, or you're running some sort of IoT scenario where, yeah, you really need that data right now, you don't want cold start. Other scenarios, it's fine. It really depends on your situation. But for that, we kind of that's kind of one of the reasons that we developed the premium plan. And what the premium plan does is you have a monthly sort of a monthly billing model for, you choose a number of instances that are basically always there, always on. They're always warm. They're ready to catch requests. You can configure how many there are, and then past that, more instances are scaled based on the serverless scaling model. So it's like you have a base threshold that you never go below, but you go up and down as needed. The premium plan machines are also newer and have more cores, so they have more processing power. And you're also, because it's kind of a hybrid of the consumption plan and the app service plan, you get some of the benefits of running on an app service plan that you don't in the consumption plan, like support for running in a VNet, which a lot of people want. Other places that functions can run, you can run a Docker image on Azure IoT Edge, so you can run functions on a connected device. You can also run functions and the runtime on other Azure components that are not app service, so AKS, Azure Kubernetes Service. You can run it on Service Fabric Mesh, which is actually where we do it for our Linux consumption hosting plan, I believe. And then you can also take your functions and your functions runtime and run them outside of Azure. You can run them on Kubernetes in your own, on your own. I'm so sorry. You can run it on Kubernetes in, say, on-prem, or on your own machines. You can also choose to just run it straight on raw VMs, just bare metal, where you have more control over the environment. And you're not in our hosting plan sandbox, which does sometimes lock down some dependencies, so that people aren't doing anything super hinky with them. And you can also take it to other clouds. So if you want to run Azure Functions on that very famous Booksellers cloud, or the primary colored company's cloud, you are absolutely welcome to, and it's totally a thing you can do. And the last place that you can run it is on Azure Stack. So Azure Stack is it's kind of for customers who really want basically their own miniature copy of Azure that they can run on their own hardware for various reasons, but functions can run there too. So the runtime is very portable. And I've kind of gone into the development experience a bit, but there's a number of ways that you can develop functions. So you can go into the portal. We have a portal creation experience with templates. Typically, this is best if you're doing like a quick demo or you're just trying functions out. For more heavyweight, like serious dev project work, we recommend going into a IDE on your local dev box. So we have support for VS Code, Visual Studio for .NET-based languages, IntelliJ for Java, and you can even just use our CLI, which we call Functions Core Tools, and just open the files that it generates in, you could use Sublime Text, you could use Notepad++, just edit directly in there, and away you go. This also kind of talks a little bit about the languages that we support, and this is slightly out of date. So we do support .NET-based languages, so that's C# and F#. We support Node.js, we support Java, but what's missing from here is PowerShell and Python. And Python was announced GA earlier this year, and PowerShell is going GA at Ignite in early November. Okay. These are some of the bindings that you can use to trigger your functions or also use as inputs or outputs. So we connect to a number of other Azure components. You can do everything from HTTP triggers to triggering off of Cosmos DB, Microsoft Graph. You can write out to notification hubs. We also integrate with some third-party components like Twilio and SendGrid for SMS and email. You can write out to Microsoft Graph, Azure Mobile Apps, Azure Storage, Service Bus, etc., and just kind of integrate with all of that. One thing that's not on this slide also is Event Grid. You can trigger on it and you can write to it. Okay, so functions is pretty flexible, pretty versatile. These best practices for the serverless programming model kind of follow from the stateless, short-lived nature of it, event-driven nature of it. I'm not going to talk about this one, but item potency is kind of important. Item potency, if you're not familiar with the term, means that for the same inputs, you will always get the same outputs. The function will always do the same thing. So if your function has side effects, for example, if your function is a blob if your function is a blob processing function that reads the blob, deletes the blob, and processes the in-memory version of the blob, you're going to have a bad time if, say, you break after you delete the blob, retry the function, and your first step is to go looking for a blob that isn't there. So we recommend that you anticipate, well, what happens if I run this again after I've run it once and it breaks in these places? This is a single responsibility principle. This is the short-lived thing. Avoid recursions. They can get kind of hairy. And just be aware of your rate limiting and your concurrency limitations because of the scaling nature. Remember, you might be going from, you might be at 1, you might be at what's our limit, like 200 or something? Anyway.
The limitation varies depending on the plan?
Yes, it does, and I don't have the hard numbers in my head. But just like be aware of what kind of scale you could potentially be operating at. Okay, so serverless is great for serverless, and functions work well for a lot of scenarios. And we see our customers doing some pretty amazing things just with the vanilla components. But there are some scenarios that are a little difficult. You can do them, but it's going to be a little complex. I'll talk about an example or two. Or in some cases, it's just, it's going to be really hard. So let's say that I have a workflow and it's very simple. I have steps that I follow in sequence. And because I want to follow the serverless programming model and have that single responsibility principle I'm following, I'm going to put each of those steps into their own function. Well, the question then is, how am I going to make sure that, if I pass a data point into function A, and function A creates a data point, how am I going to get that to function B, and then C, and then D? Well, the straightforward approach is to put a queue between every function that one function reads from and another function writes to. And that works, but now you've got, n-1 queues to deal with. You've got more resources. I have done this. I built a data ingestion pipeline in the early days of functions that had several processing steps, and I put event hubs between them instead of queues. And it worked, but the problem came when we were troubleshooting it, and we realized we didn't really have a good way to document how that system was connected. What we did have was a very large Visio file that detailed each component and how they connected. And as soon as our requirements changed, that Visio file was out of date. So the only real version of the architecture that was up to date was in my head, and that is not a place that you want to be, especially when things are going wrong on a Sunday. So this is okay, but it lacks documentation. Another possible scenario is, let's say I want to take advantage of the scaling in the cloud, and let's say I have some work that is embarrassingly parallel. So for example, let's say I have a batch of files, and each file I want to do some processing on, and it doesn't depend on any of the other files. I can run them all at the same time. It doesn't matter. So I would like to get that batch of files into one function, have that function fan out into several function executions, and then aggregate that work back in, and then I'm done. So now I'm taking much less time than if I ran them sequentially. Okay, well, how would I do this? I could, from this first function that takes in the batch, just separate each individual file and put them on queues and have those queues trigger a function that does the processing. We're back to the whole queue question again, and also, how can I tell when all of the processing is done? What system is keeping track of all of those function invocations that I've just started up? And what is pulling all of those results back together and bringing everything back in to give me my final aggregated result? It's possible to do this. You have to do some fancy footwork with timers, and again, you've got a lot of queues going on. It's not very nice. And then we start moving into some more complex patterns that are kind of just, please don't try. So external events correlation. Let's say I have a function and I want to treat it kind of like an actor model. So like I want to receive events into the function, update some sort of state. A classic example of this would be like a counter that I can increment or decrement. I would send a event to do each of those things, and I want the counter state to go up or down based on the events that come in. And I want to be able to pull that counter state and use it somewhere, so get the status of that thing. I've actually never, I don't think I've ever seen a proposed architecture for this. I'm sure people have tried. There's also, what if I really do want to run a long-running process? So, for example, if I have connected devices, say on the floor of a factory, and I want to monitor their temperature, like just check it every, I don't know, every half hour, every 10 minutes, whatever's good. And if that temperature is over a particular threshold, fire off some sort of alert. Say, hey, get over here before things start catching on fire. The question is, how am I going to keep that running? Well, we could go back to the dedicated hosting plan, but then you're paying for a dedicated hosting plan, and you don't have the potential to scale the way that you would in a serverless plan. It's also, there are some certain flexibility issues involved there. Let's say I have a function that maybe kicks off some more work, maybe it needs to, do a database call, maybe it needs to do some serious processing on something. It's going to take a long time. I mean, I'm still following single responsibility, I'm only doing one thing. It's just that one thing is a beast. So let's say I'm a client, I call that function, I say, hey, here is my gigantic file, please do your thing with it, and then what happens? I wait, and I wait, and I wait, and maybe I get a response before my HTTP client times out, but I'm just kind of standing there waiting for this function to be done. There's a better pattern for this, and that's for that function to return a response to me that says, okay, cool, I got your request. Here is an endpoint where you can check the status of your job. It's kind of like when you go to Starbucks and you order a drink, you don't wait at the cashier for them to make it up and hand it to you. They give you the receipt, and you move down the counter, and you wait there, and then they give you the drink there, so other folks can go and order. You're not clogging up the line. And then there's human interaction. So let's say that I have I have an SMS verification system. But I want to institute a timeout. So let's say I want to send a confirmation code to a user. I want the user to text that confirmation code back to me, which will trigger a function, and then I want to check, is it the right code? And based on that code, yes or no, approve or not. But maybe that user, humans are very unreliable. We have to and they move in slow human-y time, not computer time. So we have to account for maybe that person does not check their phone. Maybe they're like me and they forget their phone, and it drives people nuts because it's like, Katy, where were you? I was off the grid. I was having a nice time. Well, okay, fine. But in the meantime, your phone has blown up with notifications. So you need some sort of timeout in place. And so with all of these patterns, what you end up with is a lot of overhead just to get these going with traditional serverless components on Azure. So here's where I do the big reveal and give you a very cute bunny and talk about durable functions. So durable functions is an add-on to Azure Functions. It's the Azure Functions programming model is extensible. You can write your own triggers and bindings for it. And Durable Functions is a very advanced extension, or it does some fancy stuff under the hood, basically, that allows you to write stateful functions in a nice, you're shaking your head.
Yeah, so the whole point of serverless is being stateless, so basically you're stateless serverless, or stateful serverless now, right? So why use functions if you're no longer really serverless?
Could you mind repeat the question for the online?
Right, okay, so Ryan?
Mark,
I'm so sorry. So Mark's question was, if I want to use state with serverless, why am I using serverless? Why am I using functions, right? Well, I mean, maybe you want to take advantage of some of the other benefits of serverless. Maybe you like the serverless programming model. It's just, not quite flexible enough from your needs. We tend to try to meet the customer where they're at, and we've seen a lot of customers who want to use serverless, but the scenarios that they're looking at do require some sort of state management, and they're already doing the state management on their own. They're using Redis caches, they're using storage, and so on. And it seems to be the way that things are going, so why not make it easier? So what durable functions does is it will simplify all the transactions and coordination that I kind of alluded to, all of that overhead for managing complex patterns, and it allows you to call a function from another function either in a synchronous or asynchronous fashion. You're like, okay, that's great, but why not the queues? Well, remember the giant Visio document. If I had when I joined Microsoft, my first project was durable functions, and I was very excited because I remembered the giant Visio document, and I looked at durable and I went, oh great, you know what? If this had been around, I wouldn't have needed the document. My workflow and the way things connected would have been documented directly in my code, and anyone could read it, and I could have slept in on Sunday.
I also have my own opinion from the developer point of view. So when serverless is stateless, right, and short-lived, but that is a serverless definition. But the other function has that advantage of the coding pattern. So as a developer, I want to use in the coding pattern of the serverless, but want to break the rules of the short-lived and the stateless. I want to write some code, stateful, but still want to take advantage of the serverless way of coding. So that's maybe another reason why I want to do the durable function.
Yeah, I find it just kind of, it's just humorous to me. Like,
I don't understand. That
because
sounds
serverless is always implied to be stateless, right? And now you're basically coming full circle.
right.
And we're
Centralized
saying
consumption
we're gonna write
based
serverless that's now
brand.
stateful.
Right. It's
Like, dude, you already had that all along.
yeah,
so-
right.
It's slightly different. We'll go into some of the things that you can get, but yeah, that is a whole religious purity discussion that I am not equipped for at the moment, and I think the only way to win is not to play. All right, so let's talk a little bit about what goes into durable. So with durable, we actually use 3 different bindings in our binding model. So there is a starter function, let me backtrack a little bit. So the heart of durable really is the orchestrator function. And the orchestrator function is the function where, where you're documenting your workflow. It's like a list of steps, and then the particulars of each step are carried out in another type of function called your activity functions. And then the starter function is what kicks off the orchestrator function, and this allows you to basically trigger an orchestrator off of any of the bindings, any of the trigger bindings that Azure Functions supports. So we have Kafka triggers now. You could trigger off of Kafka. You could trigger off of blobs, HTTP, whatever trigger you want to use to potentially start an orchestration. That's what your starter function will hook up to. Okay, let's see here. Yep, so the starter function calls the orchestrator function. The orchestrator function may call several activity functions. They perform some work, and then that work gets passed back into the local state of the orchestrator, and the orchestrator either goes to the next step in its code, or ends and provides some output. So what does the programming model look like? Well, this is the chaining example I was talking about. That first upper left box on the 6 square grid. So in this piece of code, I am calling a first function. I am getting the result back from that function, and then I'm feeding that result. That result becomes my input into a second function. And the result of the second function becomes input into a third function, and that result gets returned, and then this whole thing stops execution. Now, think about what you would do without durable. You would take the result of, this would be a function, you would take the result of that function, you'd put it on a queue. This function would trigger off of, F2 would trigger off of that queue. It would put Y onto a second queue. F3 would trigger off of the queue that contains Y, and then it would output to some sort of something else, right? Here, so I've got, I've got that leaves me with 2 extra queues. Whereas here, I have no extra queues, just one extra function, and I get the added bonus of being able to see my workflow in code in a way that I'm familiar with. Another nice thing about this programming model is that because we're pulling local state back into the orchestrator, we're also marshalling exceptions from the activity functions up into the orchestrator. So let's say if F1 throws an exception and doesn't handle it in its own code, that exception gets propagated back up into the orchestrator, and suddenly now I can catch that in a try-catch block, and I can do something with it. All right.
Can I interrupt?
Yeah, absolutely.
So obviously it's quite easy to do this in code, right?
Mm.
And I really remember I tried to, I used Azure Functions a year or two ago.
Mm.
And I remember that I had to put some sort of storage in between those functions, some sort of, I forgot what you call it, like a queue or a bus.
A service bus.
I go out, get back a result,
Mhm.
and depending on the result, I have to call another function, right?
Right.
So all the time I had to put something in there.
Right.
That was very unnatural and a little bit annoying, right?
Mm-hmm.
And actually, I could have just called the Cosmos DB and store everything is JSON there. Right? And then, but I think this issue solves very well. This kind of I don't want to call it a design pattern because it's just a function.
Programming model.
Like it's a closure with
Yeah.
a bunch of functions in there. So it's probably that's very durable functions. So
Mhm.
I think it's kind of strange that they came later. They should have been always there.
Mm.
But probably it was difficult to do.
Well, depending on how much time we have, Ken-san, I can go into sort of durable functions under the hood and talk about kind of the implementation and what's going on there. And I think if we do that, that will shed some light on why this came later, and also kind of how it works.
We want to hear about Cosmos things.
Okay. All right. What time are we here at? 8:30. Okay. 8:30.
We going to?
And 9.
All right.
Goes to 9, okay.
Okay. So, all right. Well, I can go through. Let me hang on a second here. I can go.
Or as long as we want.
Oh, yeah.
I don't mind.
All right. Well, depends on you guys. Would you like me to go further into a deep dive of kind of how this works and how we achieve statefulness on a sorry.
Yeah, but I think it might be okay for the overview this time, and we can go for the detail.
Okay.
Yeah.
Okay. Sounds great.
Near future.
All right. So
I
let me
think
just.
We also welcome the remote speaker.
Yes. All right. Let me just skip quickly through these slides. Blah blah blah. And okay. So,
Bring back to my deck now.
okay. Yeah. So check out durable functions. It's aka.ms/durable functions. Play around, have fun, and see what you can do with it. Thank you for your time.
Thank you. All right, so let's take 5 minutes break. Then after that, we continue for the Cosmos DB. Yep. Please coming back like 8:35.
So when did you get here today?
No, Sunday.
Sunday? You're
But,
still jet lagged?
Yeah, she wake up late to prepare for the presentation as well. And you guys are living the Seattle temple anyway, right?
Yeah. But I just sleep on the plane and I get here and I'm
I
good.
did sleep on the plane.
Yeah.
You did?
Oh yeah.
You're still jet lagged?
Look, I don't explain how my body works.
It's easier going west. It's going home that's the one that sucks.
Yeah. Well, I get in Sunday.
Actually, you should let me present because I've got demos.
Right, because we are doing the YouTube stream. And do you have like the ORB Studio installed in your computer?
They're actually on a VM.
Okay, so if you can
So,
log
tell
in
you
from
what.
here,
Uh,
do you have the access? Right, IP address and
you
Using
can
password.
RDP into that IP.
using that. The C2.
Let me get out of there. Hold on. Anyway, I don't run anything local on my machine.
Yeah, that's good.
I work for Azure.
Yeah,
It's
that's
kinda
brilliant.
stupid saying, oh, it's just on my machine.
It is yours?
No.
Is it yours?
Yes. I'm so sorry.
Plus, I don't trust Windows. I've gotten burned too many times.
Yeah, I know. And just okay.
That should show my.
Yeah, and we only the
It's awesome.
showed the other side. So if you can.
So what's the KVM to get back and forth, or just duplicate?
Yeah. I try to avoid.
I go
duplicate.
back. I go back and
Yeah.
forth pretty quick in this. So
Right. Yeah, I know what you mean. Well, okay, so
just
yeah.
duplicate. It's easier for me.
Right. The thing is, I try to avoid doing the duplicate. This is my working computer anyway, so.
Can you just do a separate desktop and throw everything on that, and then
Yeah, sure.
then we won't reveal all of your secrets,
Yeah.
Ken. Let me grab a bottle of water.
Yeah,
and then
sure.
we're good.
All right. So I wish this is yeah, you know how to do it, right?
Oh, I know how to run my own demo. So what am I doing to switch between these screens here?
Yeah. So just
Just
this
the
one, this
just
one.
the tab
Yeah, two
or
and
just
three.
the
Yeah.
keys.
Right. So
Shift key or control key?
control Windows, but if you full screen, you cannot coming back. So maybe you stay with this size. It may be easier.
Sure.
Indirectly, just Windows control and right and left.
Okay.
Yeah.
Easy.
And let me just resume. Yeah. It should be. And let me double check.
I got Cosmos stickers.
That's cool.
Sorry, folks. Mine don't get any stickers. Only those that show up. I got two flavors. I got round ones. And then I got ones that are not round. Very well wrapped. Yeah, so I got these ones. And then I got the round as well. So everybody take one for yourself. You can take a couple and then put them on your friend's laptops when they're not looking. Of course, without permission. Without their knowledge at all until it's too late. So
Yeah, I try to connect back now.
yeah, sure.
Come on. Update already. Who is that?
Huh?
Is it coming from who?
No, it's me.
Okay. I understand. Yeah, no worries. Thank you for. And do you know how to get out from here? Cool. Should be- Let's see. Yeah, I just want to make sure it's coming to the YouTube. Come on YouTube, you can do it. There you go. All right. So
set?
yours, yep, all set.
Okay.
And this is your microphone. And if you want to use this one,
Can I use this one
yeah,
instead?
sure, of course. Yeah.
It's easier if I don't have it to hold my hands. All right. All right. Thanks, Ken.
Yeah, sure.
All right. Hey, everybody. I'm Mark Brown. I'm a principal program manager on the Cosmos DB team. I want to spend the next kind of 20 minutes talking about how to build distributed applications with Cosmos DB. So if you're building applications in Azure for the cloud, by and large, these may be, or maybe should be, distributed applications that are running in multiple regions within Azure. So a little bit about Cosmos. So Cosmos is Azure's globally distributed, massively scalable, multi-model database service. So fully managed. You don't manage disk, you don't manage CPUs, you don't manage memory. All you just manage is your model and your data. Cosmos is multi-model, so we support different models that are emulated on top of Cosmos's core SQL API, including etcd. We support our table API, also Cassandra, Mongo, Gremlin, and then we also have a new layer for Spark. Some of the key attributes about Cosmos DB is we have turnkey global distribution built in. So if you want to replicate your data into a different region in Azure, you just simply click a button in the portal, and we'll replicate all your data there for reading and writing. We also provide elastic scale-out for throughput and storage. So you go and you provision the amount of throughput you want, and with Cosmos, it's a provisioned throughput, so it's not a serverless like Katy just talked about. You provision the amount of throughput you want for your database, and then you get that amount of throughput guaranteed. And that's guaranteed with an SLA. And we have two SLAs. We have one around latency, so we're the only database service in Azure that provides an SLA around latency, and that's less than 10 milliseconds for reads and writes at the 99th percentile, and around 3 to 4 or 5 milliseconds at the 50th percentile. We also provide 5 nines of availability, so we're the only data service in Azure that provides 5 nines of availability for your data within Azure. So, I talked about wanting to build distributed applications. Why would you build distributed applications at all? And the first reason is for availability. If I deploy an application into, say, Japan East, and Japan East has an outage, what happens to my application? It's no longer available. So if I want to increase the availability for that application, I should deploy it in N+1 regions. So maybe in Japan West, or Korea South, or in Southeast Asia, or in US West. The more distributed I can make that, the more isolated it is from any potential incidents or events that are happening, whether it's a typhoon or just some power outage or networking or anything. So availability is increased when you deploy multiple instances of your application and then distribute those from some distance from each other. The other reason you would build a distributed application is for latency. And the idea here is the closer your data is to your user, the faster the performance is going to be, right? So customers do this when they use a CDN for, say, their web applications, and they want to edge cache as much of their scripts or their images or whatever as close to the user as possible. This prevents it from having to go back to the origin server each time to get that. You can see it helps with performance with web applications. Do that to your data in a real application, or in a real application, and say a business application where you have customers reading and writing data to that, you get that same benefit, right? So the further the distances that the data has to travel, the faster your application is going to perform. So that's why you would build a distributed application. Distributed applications themselves have some limitations. And to understand a little bit of those things, I'm going to go into a little bit of science here. So 3 concepts I want to talk about when building distributed applications. All 3 of these things are intricately tied to each other. There's consistency, latency, and availability. All 3 of these things are super important and absolutely tied together. Now, when I talk about consistency, this is what most people think about, is consistency in terms of an ACID transaction. In a distributed environment, in a distributed system, that's actually not what consistency is referring to. Rather, consistency means the uniformity of data that's separated by hundreds or even thousands of miles. That's what consistency means in the terms or in the context of a distributed system. Okay, all clear? Okay, so some science here. in a distributed system, there's a theorem called CAP theorem. Now, a guy by the name of Eric Brewer, who's a computer scientist at UC Berkeley, came up with this thing to describe what happens in a distributed system. And what it says is that in a distributed system, you can only get 2 out of the following 3 things. You can get consistency, so I always get the most recent write within that system, or I get an error. Availability, every request receives some response, even if it's not the latest data. So I could receive the data or receive an error or out of date data. And then also partition tolerance. So the distributed system will continue to work even if there's a network cut between the nodes within that system. So this is what CAP theorem says. You can only get 2 out of those following 3 things. So let me illustrate this with a bit of a decision tree. So if I have a network cut or a network partition, yes, I have a choice to make between 2 things. I can choose availability for that distributed system, or I can choose consistency for it. Still confused? Let me help here with this illustration. So in this scenario, I have a master node here and a replica node here. In this scenario, I am choosing availability for this system, okay? So I'm going to write 5 into my master node, and I'm going to replicate it over here. So I have no network partition. The network is working. The nodes communicate with each other. However, if I have a network partition and a network cut between these 2 things, in an availability system, I'm going to write 6 here, but I'm still only going to read 5. Why? Because I'm choosing availability for the system. I'm making a choice that I want the system to be available, and I'm foregoing consistency within the system. Make sense? Let's choose consistency in this model. So I have same system here, everything's working fine. Write 5 over here, get 5 over there. Now I cut the network between these 2 nodes. And in this model, where I have to have consistency between all my nodes, I write anything into the system, I have to produce an error between those 2 nodes. I can't maintain consistency. Those are the choices you have to make in a distributed system with CAP theorem, okay? Now, CAP theorem is great because it describes the behavior or the choice you have to make when you have a network partition between 2 or more nodes within a system. It doesn't describe everything that happens, though, within a distributed system. There's actually some other stuff that happens as well, and you have to make another choice. This is what PAC-LC theorem talks about, and this is an addendum to CAP theorem and came about 12 years later. So in about 2010, this was postulated. And what it says is that in the case of a network partition in a distributed system, you still have to choose between availability and consistency, just like CAP theorem says. But even when everything is working okay, you still got another choice to make, and that's latency and consistency. So let me illustrate this. Here's my decision tree, right? Here's CAP theorem over on the left, and then this is what PAC-LC theorem looks like over on the right. So even when there's no partition, this is my these are my choices here, right? Now, still confused? I'm going to illustrate some more. I'd like to animate everything I got here. So in this system, I'm going to choose consistency for my distributed system here, okay? So in my master node, I'm going to write 5. However, while that 5 is being written in a consistent system, distributed system, what has to happen? I have to stop anything else from being written or done to the system until I replicate that data and commit it durably. So in a distributed store where I'm maintaining consistency, everything must be consistent before anything else can happen. So that data then has to be replicated, committed, and then act back before I'm consistent, before I can do anything else, right? The problem here is that when I have nodes that are separated by hundreds or thousands of miles, I have an issue with latency, right? So I'm choosing consistency in this model, but I'm foregoing latency. Now, let's say I choose latency in this model. Well, fine, so I can just write data into any node. I don't care. There's no problems with latency because I'm not having to replicate and commit it into every other node within the system, right? So I get high latency, or low latency, excuse me, in this kind of scenario. Okay? Everybody confused? Hopefully, online everybody?
Just a bit.
A little bit confused?
Yeah, just a bit.
Okay, let's do some demos and see if I can help show you. So, as I said earlier, with latency, the lower the latency, the better the performance of the application. And the way you achieve that is to get your data as close as possible to users. Okay? So in this demo, I'm going to show read latency with a single region account versus a multi-region account. And to illustrate this, I have a master node set up, one region account, Cosmos DB set up in East US 2 with, say, a fictitious web ad over there. And then I have a VM sitting over in West US 2. It's about 2,000 miles away. I don't know how many kilometers it is, but it's a lot. And I'm going to try and read data from that. I'm then going to show you, and I'm going to show you the read latency, so how long it takes. I'm then going to show you what happens if I replicate that data to that same region and then do the same number of reads and show you what that latency looks like. All right, so Control Windows, right key?
Yeah, right. Yeah.
Here we go. Okay, so I'm going to test 100 reads. This is a single master account with a read region in East US 2 from my VM, which sits 2,000 miles away in West US 2. And 70-something milliseconds. Not too bad, but not too fast either. In fact, let me show you what happens. If I do the same test, this is a single master account, but now I have a read replica in West US 2, and I'm going to do the same 100 reads from that same VM. Right? 2 milliseconds. Average 3 milliseconds. But you can see that's a massive order of magnitude difference, right? And the reason is because the data is that much closer, right? Okay, so there you go. Average latency, 74 milliseconds versus 3 millisecond latency. Okay? So that works great when you do a read replica into another region. So that's a single master account. So all my writes go into East US 2, and then I'm reading from East US 2, and I can read from West US 2. So that works good in a read operation, but by and large, most applications have to write data too, right? So how do I reduce latency for my writes? Because if I try to do that, I'm still going to end up with that 70 millisecond, and that may be too high for many applications. So how we get around that is with multi-master in Cosmos DB. And what this does is that it makes every read replica within your data store fully writable. Now everything is a full master within there. So you can write into any one of your replicas in any region, anywhere in the world, and it's essentially like it's writing to its local store. And then we will replicate that and then merge all the conflicts for you within there. This is great because essentially what you can do is use Cosmos DB to get, frankly, unlimited endpoint scalability. If I need more write throughput, I can increase throughput within a region, but I could also just add more regions and then load balance over all of them. So if I've got IoT scenarios where I've got millions or billions of devices that all need to write, then just load balance geographically like that. Just add more regions and then just load balance over them. So this is very powerful in what you can do with it and just the amount of data you can ingest with it. So let's do some more demos. So I'll show now you write latency for a single write versus a multi-region write. So single region write, I've got my write region in East US 2 over on the right side, and then my read region over there. So I've got to write and come all the way back versus multi-region write, I'm basically just writing into each region right there, just like it's local, okay? So control window this.
Yeah, and a quick question. In that scenario, where the client, in the east side or west side?
It's in the West US.
West is, okay.
Yep. So here I'll test 100 reads, single master account. This is fast. We just showed this, right? That's in West US 2 read replica. My VM is in West US 2. Now let's test 100 writes. So read replica is West US 2, but my write master is in East US 2. Slow, right? Because I got to go all the way across 2,000 miles, whatever, 3,600 kilometers to get over there. Okay?
But you still read from the east US 2, right?
I can, well, from that one, I was reading from West US 2,
Okay.
right? Because it was fast, right? 2 millisecond latency, right? But writing to that single master account, I still have to go 2,000 miles to do every one of my writes. So my write latency is terrible.
That means when you write into the east US, it's duplicated to the west US so that you can read from West US.
That's right. So I'm writing to West US2, and then I'm reading back out of writing to East US2, and then reading from West US2. Yep. Okay, so now I'm going to test 100 reads. This is fast, of course, because it's still in that local region for West US2. But now let's see what happens to my writes. Right? Super fast. So I'm not getting 70, 80 millisecond latency for my writes now. I'm getting 5 millisecond latency for my writes. Right? So massive performance benefit when you run a multi-master type of configuration, and you have requirements around low write latency for your applications, right? It's just like it's writing to its local database, right? All the replication just happens behind the scenes. You don't have to worry about it. Your applications are going to respond much, much quicker. Okay, back to slides.
Yeah, one quick question.
Sure.
So from the client is on the west, right? When we write in the data to the east data center, it takes time because the client just sits in the west, right?
Yep.
And the data is replicated back from east to west so that we can read from the west, right?
Mm-hmm.
But now you are writing the data to the west, and we read the data from the west, but still the data is already replicated to the east side, right? The reason why that is working faster is that because two databases, the west and east, is connected back by the other data center, which is way faster from client to server.
No, the reason it's faster, the reason multi-master is faster is because if my app is sitting in West US, I'm writing to that node that sits in West US. Okay? In the previous model, so here's the distinction is single region write. Here's my master, and then I have a read replica in West US.
Right.
I then have another application or a VM sitting here. So I can read and get fast reads, but if I have to write any data, all that data has to flow back to here. Versus a multi-master, I can read from here, but now I'm writing to here. And then that data is replicated to this node or any other node within the account.
Right, and what happens if I have a client on the east side as well, and when we try to read the data from the east data center, when you're writing the data to the west data center, is the replication happening instantaneously, or we just...
It's not instant, it's driven by the consistency level you choose.
Okay, so that's a consistency for the...
Correct. So, and remember, we talked about consistency levels. If I choose strong consistency, what happens to my latency? Does it go up or down? Yes, your latency goes way up, right? Because now I write something here. It's just as bad as if I was running a single master. So if I'm running, and you can't do multi-master strong because it doesn't make any sense, right? If I have to write it, I mean, you can't cheat. This is basically a speed of light problem, right? The data's got to get to all those places, and it takes time to do that. So, all right, we talk about consistency. Let's talk about consistency. So, as I said, consistency is not consistency in an ACID transaction. It's consistency that governs how your data is replicated and maintained as uniform over a huge amount of distance, right? Cosmos, there's 5 different consistency levels you could choose from. Strong is just like the name implies. Everything is absolutely perfectly consistent in every single node across the entire universe of your account. Bounded staleness is a relaxed level of consistency that's bounded by either a function of time, usually in seconds, or the number of updates that happen. So when you define bounded staleness as a consistency level, you have to define both the amount of time and also the number of updates that you're willing to tolerate essentially within that system. And then what Cosmos will do is that it'll make sure that it always keeps that window within that and guaranteed within that. Session level consistency, this is the most used level of consistency, and in fact it's the default. And the way to look at session level consistency is essentially it's an in-region strong for your application. It also has a feature called a session token within there, which is functionally the log sequence number for the writes that happen within there. So you could actually pass a session token between clients within a region, and they will always maintain, they essentially inherit the strong consistency that you would get for the right client. So in a session level consistency, you always read your own writes. There's no dirty reads ever, right? And they do that by maintaining this session token because I always know what's the LSN for my last write within to the database, okay? I can pass that around and then also allow other clients within that region to have that same level of consistency. Kind of a common use case scenario is I have a load balanced kind of stateless application. Sorry, I have a load balanced application. Okay. I can't believe people can't hear me because I'm so loud.
Yeah, I mean, people can hear you, but
Oh.
online people
Oh,
cannot hear
okay.
you.
Here, you know what? Let me just stand by the podium.
Okay.
Okay, so sorry, online folks. What was I talking about? Session level consistency. So you could actually pass the session token around to lots of different clients that were in, like, say, a load balance kind of scenario, and they can share that, and then everybody can use the same level of consistency. Nobody gets a dirty read. Anything outside of a session token or within that is going to get eventual consistency, even within the region. Although within region, that level of the interval for dirtiness on those reads is frankly milliseconds. It's not a huge deal. Consistent prefix. This is a more relaxed level of consistency, and it's defined by basically knowing that every update you get will be in order in which it was written. And then there's eventual, which, as the name implies, means everything eventually is consistent, and then there's no guarantee on the order in which you get them. So you could write 1, 2, 3, and you could see 3, 2, 1. So it's the most relaxed level of consistency. What you will see in terms of the actual consistency level within Cosmos is bound by two things. One, the consistency level you choose, also by the amount of write throughput or write volume that you're doing, right? So we maintain for relaxed levels of consistency, maintain that consistency using unused throughput. This is true for all except for bounded staleness, which because there's a rule that says you cannot go over 5 seconds, right? Or over 100,000 updates. For strong, right, we have no choice whatsoever. It's basically synchronous replication, not async replication at that point. Everything else is essentially driven by it's a function of the throughput that you've got provisioned. So if I provision 100,000 RU and I'm consuming 100,000 RU, there's not much RU left to manage the consistency within that. So that consistency is going to get further and further behind, right? So we'll catch up to it. Generally, you don't find applications that are consistently throwing or saturating throughput in such a way. Usually they write a bunch of data and then they don't do anything. Or maybe they do a level stream of stuff, but they're going to provision above that because they may have spikes. So anyway, you want to monitor that and maintain that or see what that looks like. Generally speaking, if you write a kilobyte of data in Japan East, it's going to be replicated in milliseconds to Japan West. It's generally that fast. And it all runs on our backbone. Okay, enough of that. Latency versus consistency. There's a direct relationship between these things, right? I think I showed you with strong level of consistency, right? The stronger the consistency, the higher the latency. And it's more pronounced the greater the distance. So in fact, and I mentioned this earlier, you don't often have to think about this when you're designing software, but in a distributed system, the speed of light can become a problem because the further the distance, the longer the latency is going to be for your application. Okay, enough on that. Consistency versus throughput. Within Cosmos, the consistency level you choose has impact on the amount of throughput you get on your read path. Now, on the writes, for strong level consistency, this is what's called a global majority. That means that everything globally, you have to have a majority for quorum for that to be committed, okay? Within all the other levels of consistency, so bounded staleness and less, within region, it's a local majority. That basically means that you're going to write and commit to 3 of the 4 replicas. So within Cosmos, we have a 4 replica set, okay? And you have a leader, 3 followers, and then one of those followers is a forwarder. That guy's job is to replicate data to other regions. So I write in data, single piece of data, I'm going to commit it to 3 of those things and then ACK it back. Now, when I read data back using session or less level of consistency, it's just a single replica read. And that's why it's just a single RU within there. So if I read a single K or less of data, basically that's a single RU within your application. If I use a stronger level of consistency like bounded staleness or strong, That's a 2RU read, and the reason is because we do a local minority read. And this is, in fact, how we guarantee consistency, is we're going to read from 2 replicas, and if the LSNs from these 2 match, then yes, we agree that's the latest data and we return it back. If they don't match, then we return the one with the higher LSN, because we know that's the more recent write within there. So that's how consistency actually is maintained in there, and why a read using bounded staleness or strong is a 2RU read, because it's actually, each of these things is in fact its own little piece of compute, like its own little computer or VM within there. Okay, one other thing, we also do what's called a dynamic read quorum. What this means is that if I have 3 or more regions and I'm configured for strong consistency, and one of these regions fails, what would happen if you didn't do this? You'd actually be out, right? Because in a consistency model, you have to be able to replicate to every region. So if I lost a region, a read region in this case, I'd be down, right? What we do, if you have 3 or more, so if you have an account, strong consistency, and I'm running 3 or more regions, we do what's called a dynamic read quorum. So let's just say I lost that guy right there, I don't know who it was, that's East Asia and Hong Kong. Let's just say that one went down. We'll actually take it the lease, expire the lease off it, and then continue to replicate to all the other regions. And then when it comes back, we'll just replicate and backfill into that one there. Of course, if you lost your write master, that's not the same, and I'll talk about that in a second. But this is very helpful and not very well understood by people, is that we do a dynamic read quorum. Okay, I want to show you another demo. This is consistency versus latency, and then consistency versus throughput. So, I have an account, write master in West US 2, and a read replica in Central US, 1,000 miles away. And I'm using eventual level consistency, so I'm optimizing for latency here, okay? I'm then going to show the same test, but I'm going to use strong consistency here, and I'm going to show you the throughput, or the write latency for that. And then I'm going to double the distance, and I'm going to show you that. And then I'll do another test. I'm going to show you the read throughput for eventual consistency, and then that throughput for strong consistency. Okay. What am I doing on time? Am I good? Okay. Oops. Okay, so I'm going to test 100 writes. This account has got eventual consistency. I'm going to write into West US 2 from my VM in West US 2, and I'm going to replicate it to Central US 1,000 miles away. Who thinks this is fast, by the way?
Compare with what?
Compared with anything else you've seen today.
So this is eventual, right? Eventual is supposed to be very fast for the right.
Okay. It's fast, right? Because I'm using eventual consistency. I don't care about maintaining consistency. So I'm just blasting data as fast as it'll go.
So I can get the sticker?
You get a sticker. That's all you can. I'll get you an extra one. All right. Now I'm going to do a test. Same 2 accounts or same regions. I'm going to use strong consistency. So is this fast or slow?
Slower.
Right. Slower, because I got to write it, replicate it, and then ACK it back. Yep, 62 milliseconds. Okay, now I'm going to do the same test again. This region is twice the distance. How much slower is this going to be? Same. You think it's going to be the same latency?
This is strong, right? Then double. Right?
It's double?
Yeah.
Yep. Double the distance, pretty much double the latency. It's pretty much a 1-to-1 relationship between these things. You can't cheat the speed of light.
Yeah.
Pretty much. Yeah, so 112 RU, or 112 millisecond. Okay, so now I'm going to show you, this is just going to test 100 reads, and I'm going to show you read throughput on here, right? So, right, 1 RU charge, because I'm just using relaxed eventual level consistency. Now I'm going to show you the read throughput on strong consistency. That's 2 RU, right? Because I had to hit 2 replicas to do each of those reads within there. Okay? All right. Last topic, availability. That's weird. What happened there? I just went through, just restarted all my slides.
Yeah, and just moving forward, I just want to make sure one thing. So we tested for the eventual on strong, right? But as soon as you finish the eventual, which meaning if you read the data from central or even east, the data might not be synced yet, right? Some data could be some data is missing yet, and it eventually synchronized.
That's right. So in a distributed store, this is why the consistency level matters, is it helps define what your expectation is in terms of when data is there, right? So
and strong as soon as you finish writing, when we read the data in the different data center, the data is there.
right.
Okay.
So when you're thinking about what consistency level you choose, I think a lot of people initially think I must have strong consistency. That's 90% of the time, that's not necessary. Generally speaking, customers work on data that's local to them. And you don't need something that some customer did in one part of the world, needs to be immediately aware by everybody else everywhere. That's generally not how applications or systems need to work. There are some exceptions to this, so it's not every case. But you need to think through what is your tolerance or what are your needs around that in terms of having consistent data. And then you need to test. This is true for any distributed system you work on. You have to actually test the thing to see how it actually performs in a real wide area network, just to see what your performance is going to be like, just to see how much time it takes data to replicate, under what conditions, all that stuff. So anyway, your mileage may vary, and it's important, of course, to test and instrument all of these things. So let's talk availability. This is my last topic. So anybody that's ever built any kind of system in Azure has probably seen something like this. This is just kind of your general reference architecture for building something that's highly available. And this provides availability in multiple different ways. You have your browser, device, mobile phone, whatever, connecting you over the internet. I'm going to deploy into multiple regions because I want to provide resiliency at a regional level. So if one region goes down, I don't care. I'm using a DNS load balancer like Traffic Manager that's going to route my traffic both on the basis of where my customer is to make sure that's the lowest latency. So I'll route them to the nearest region. But if a region fails over and is no longer available, I want to redirect them to another region so they can continue to work fine. Within the region, I need additional levels of resiliency. So at each of the logical tiers, I'm going to have a pool of IP addresses, and I'm going to have a bunch of VMs in there, and they're all going to have load balanced request over all of them. This is a very well-worn pattern where I've got an app gateway or something, so I'm doing SSL termination, and then I'm load balancing over a bunch of front-end web apps. I'll then use Azure Load Balancer internally and do IP load balancing over a bunch of VMs that are also sitting within a pool. And then at the database layer, you would hopefully be using Cosmos DB in a single or at least, or even more preferably, a multi-master configuration where Cosmos is replicating all of this data between all of the regions wherever it's written, such that if any region ever goes down, that's fine. It doesn't matter. Where customers are redirected to another region, and all of their data is happily there, and they don't know anything different because of it. So that's kind of the high availability and how you want and scale within that way. And just like within a region for a logical tier, like a web tier or a middle tier, you want multiple VMs in there to provide availability in case one VM goes down, you're fine. This is what you have with Cosmos, the in-region redundancy and the replica sets. We have 4 copies of your data within there. These are all distributed across update and fault domains. If any of these ever goes down, and of course, if we update the software on them, and we do that all the time, we'll take one of the replicas out and then substitute another one back in and backfill the data, and then you never know whatever happened. And because we run 4 within here, you're always available because we only require 3 to do any commit within Cosmos. Okay, so who knows what RPO stands for? This is my last topic, and then I'm done. Anybody want to take a crack? What does it define? What's the RPO stand for? All right, I'll give you back. RPO is recovery point objective, and what it means is how long did you lose data? RTO is on the other side of that coin, and that's recovery time objective, and that is essentially meaning how long am I down for? So this is a good way of illustrating here. Both of these things are a function of time, right? An RPO is typically, when did I do my last backup? Or when did I last get my data durable somewhere where I'm not impacted by some sort of disaster? And then RTO is basically, how long does it take me to get back to where I'm actually up and available again, right? So if you're designing applications or architecting applications, and you're working with your business users or even just internally, these are two numbers that you should understand pretty deeply, right? How much tolerance do I have for lost data? Is it 0? Is it a minute, 2 minutes, an hour? And then RTO, maybe even more critical, is what's my tolerance for downtime? Like if my application crashes, my server crashes, my region goes down, what can I be down for, right? And those are usually a function of the business, right? Like every minute we're down, we lose a billion yen or whatever. Who knows? But it's usually a function of that. And then same for RPO as well, right? How much data can we tolerate to lose, like customer accounts? I mean, oh, sorry, your order's gone, or I don't even know who you are because we lost your customer account. So these are important to know. And I'll tell you why, because we actually publish our own RPO and RTO for Cosmos. And something I want to point out to you. So let me go through this table. If you're, say, you have, or you come to me and you say, I need really high uptime, like really like near zero downtime. And I say, how many regions are you in? And you say, 1 region. I'm gonna say, nonsense. I go, you cannot be highly available and wanting in a single region. One, because it just doesn't make sense in terms of the cloud. Regional events happen. Regions go down, they become unavailable. For Cosmos, our published RTO is less than a week. Now, that doesn't mean it takes a week if you just have an account in a single region for you to get it back, but this is what we publish, right? Because there's really all bets are off. You do not run anything that's supposed to be highly available in a single region in Azure, anywhere, ever. Your RPO is, for a single account in a single region, is 4 hours. 4 hours is the interval from the last time we took a snapshot backup of your account. Now, you can go and do these more frequently, but that RPO is still pretty terrible at 4 hours. You could get it, I think, down to 2, right? But that's not really acceptable for a high-performance, mission-critical application. Where it gets better, and what you should be doing for applications that have high availability, I'll get closer to the mic again, is running in multiple regions. So for a multi-region account...
Sorry, before going to multi-region, when you say region, it's a kind of Japan East.
Sure, I'm running in Japan East and Japan West.
It are 2 regions.
2 regions.
Okay, so we said 1 week for 1 region down to RTO, meaning we try to recreate the data center within 1 week.
Yeah, I mean it could be
Sounds crazy.
Rebuilding. Let's go get the construction guys.
Yeah.
No, hopefully not.
Put some radios. But yeah, I understand what region mean here. Okay, thank you.
Yep. So multi-region. So just say you're running Japan East and Japan West, single master account. If I'm using a relaxed level of consistency, so session, consistent prefix, or eventual, I get an RPO of about 15 minutes. That's roughly the upper bound of what those relaxed levels of consistency will take to replicate data between 2 data centers anywhere in the world. Japan East and Japan West, generally speaking, it's in seconds or less. But again, it's a function of how much data you're pumping in, right? If I'm writing a gigabyte of data into Japan East and trying to replicate that, and I'm at the maximum of my throughput, that data is going to lag behind somewhat, right? But that's generally the RPO is 15 minutes. Your RTO for a single master account is 15 minutes. That's the amount of time it takes for us to fail over your account from its write master and then promote a secondary read region as the new write master. So that's the function of a failover, is your RTO there. Your RPO for bounded staleness is what we call K&T. That's the interval, the time interval, and the number of updates, right? So remember, bounded staleness is defined by time, seconds, or updates. So that's your RPO, is defined by how you set those 2 values. RTO is the same. RPO for strong is what would you expect, right? It's 0, right? Why? Because if I write into a region, immediately replicate to another, and then that first region goes down, then I've lost no data, right? RPO 0. So that's cool. Where things get awesome, and what I love, is when you use multi-master. Because if I use multi-master, my RPO is still going to be the same, but for these two different levels of consistency, I get an RTO of 0 now. And how we do that is with our SDK client. So when every region is fully writable, there is no failover. And in fact, if you're using our SDK client, what happens is if it tries to write into Japan East and then it doesn't get a response from Japan East, it will retry that 10 times. And then if nothing comes back, or it gets a 500 or something else, or a 400 or whatever comes back, it's going to retry it into your next region. And if that's in Japan West, then it's going to retry in Japan West. So there's 0, you get basically an automatic failover that happened within the context of your single request. So there's no downtime. It's RTO 0. The only thing you're going to see is a little bit of latency while the client figures this out and then redirects. And then it will just keep writing to Japan West until Japan East comes back, and then it will eventually redirect and then start writing back in Japan East. So that's your RTO 0 within there. I want to point out, I said this earlier, there is no multi-master strong, right? It makes no sense. You get 0 latency benefits running multi-master strong because you have to replicate to every other region anyway. So back to my original, at the beginning of this talk, if I'm thinking about cap theorem, so what do I have to think about? I have cap theorem, so I have consistency and availability, right? My C and my A. If I'm focused on RPO, what am I optimizing for in cap theorem? Is it consistency or availability? Really? Are you sure? If I want RPO 0, how am I optimizing for availability? I'm optimizing for this, right? Right. If I need RTO 0, what am I optimizing for? That's availability right here, right? So these numbers matter when you're trying to build a distributed system. They matter for any system, but in distributed storage, they actually have a direct correlation into cap theorem because they tell you exactly what are you optimizing for within your system.
Yeah, because RPO basically saying how much data we can lose or we shouldn't lose, right?
That's right.
And RTO is how fast we can come up again.
That's right.
Regardless how much data we lose, right?
That's right.
Okay.
Data loss versus downtime.
Yeah.
Right? And by the way, can I have RPO 0 and RTO 0?
Yeah, there is one on the bottom.
No, but can I do this and this?
Is that the same as the NA on the bottom?
No,
Which strong?
I just put NA because we don't offer this.
You don't offer?
No, you can't do multi-master. We did, we used to, but we took it away. And the reason is because it absolutely makes no sense.
Okay.
Right?
That's the RTO.
If I am multi-master strong, let's just say I go back to my 2 regions, West US and East US. Remember how fast those writes were in West US? If I have to replicate that synchronously and then replicate it back, it's the same latency as if I'd just written it to East US.
Right.
It's the same. So I get 0 benefit using multi-master strong. So we just took it away.
Okay.
So can I get this? Back to my question. Can I get this RPO 0 and RTO 0? What does cap theorem say? No, that's right. I have to make a choice. There's
for the reading.
For nothing.
No?
It doesn't matter, read or write.
Okay.
It doesn't matter, read or write. So cap theorem says I can't. I have to choose. I cannot have RPO 0 and RTO 0. You can get close, right?
But what happens when we lose it? So if it's a single master and the merge read, and if you lose a single master with the write, but we can still read, right? Or we can.
Sure, you're right. So your client will fail over to a read region, but you've lost your ability to do writes.
So read for RPO 0 is possible, but
you're functionally down. Your RTO is still going to be 15 minutes.
Write anything, right?
Right.
Okay. And if we lucky losing the read replica, we still keep going. Right?
Yeah, if you lose a read replica, the client will just find another client. That takes
Slower. Right?
30 seconds.
Because there is a kind of try and fail over.
There's a TTL for the connection in there, and it'll refresh every 30 seconds, or it may be down to 10 seconds now.
So can we consider that 30-second RTO, or from Cosmos DB point of view is 0 RTO?
Sorry?
So can we consider that 30-second is 30-second RTO, or from the Cosmos DB point of view is 0 RTO?
So your availability is still there. It's just a retry figure within within the client. So you're not getting an error back. There's no loss of availability.
Okay.
So I think that's it for my my talks. All those demos I showed you is actually up on my GitHub repo. So you can go and you can download them and play with them. It's very easy you can deploy the whole thing with an ARM template and then just get a VM in WestUS 2 spun up and then copy the project over and just copy all the account values into the app config. All good to go. Here's some great articles that I wrote on global distribution consistency and high availability. So please feel free to check those out. They're a little dense, but then these building a database like this is kind of dense stuff.
Right, so 2 questions if you don't mind.
Yep.
One from online, one from me. The one from the online is my good friend, another Nakamura-san mentioning, I have one question. When the product team, I mean you guys, release the relational semantics, in other words, when can I use Cosmos DB as a RDBMS? Do we have any plan which you can review to make the Cosmos DB as relational database?
Relational? No.
Okay.
That will.
Yeah, that's what I already answered to the online that I don't think so.
Yeah, just to be clear, and I didn't talk about this, we are a JSON NoSQL store. So we are a horizontally partitioned JSON store. So definitely not relational. We do support a SQL-like syntax for reads, but you use our SDK, hopefully our .NET Core SDK, and you can do reads and writes out of Cosmos that way.
Yeah, but a good try for the question in this case.
Yeah.
Thank you, Nakamura-san, for your question. My question is, from your experience, which area we start talking with the customer? Oh, I know that depends, but are you talking with the consistency first, or are we talking about the throughput performance first? When we talk with the customer, which area you recommend to?
Boy, when I talk to customers, the first thing I talk to them about is modeling.
Modeling, okay.
It's the part that customers struggle with the most because they come from relational backgrounds, and they try to use Cosmos like a relational, like a SQL database.
So way before the high availability or the throughput or the which strong or the event, we start from modeling anyway, right? Yeah,
it has to start with modeling because it drives everything. And the way to think about how to model your store is to think about first of all, what data are you operating with? And then what are your access patterns? Like, what does your queries look like? What are your where clauses for those queries?
Right.
Stack rank, just get like your top 10 queries. Like, these are the queries I run the most. And then this is the way I write, or this is the data I'm writing. Once you figure out how you access the data, and in what groups you access the data, you can actually start to come together with what does a model look like, and how do I want to model my document data for that. And then part of that is, because a lot of this can be hierarchical data, right? So like a customer can have multiple phone numbers or multiple addresses or multiple email addresses. Do I want to embed that data inside a single document? Because in JSON I can do that. Right. Or do I want to reference that data as a separate row? Like, you'd be okay putting like multiple phone numbers or email addresses for a customer in the same document. But if I was writing a blogging platform, I would not want to embed comments for, say, a post. Yeah. Right? Because if I write like post about my grandma's recipes, then probably not many comments. But if I write posts that are like make people angry and I get
Yeah,
like
right.
on Slashdot and I get 1,000,000 comments,
Uh-huh.
then I'm going to blow up my document because
Yeah.
your document only can be 2 megabytes in size.
Sure.
So I should write, my model should be write a document schema that's a post, and then put a property and say entity type,
Okay.
and say that's a post.
Mm.
And then have a similar schema that's a comment, and then put a property in there that says comment type or entity type.
Right.
Now what I can do is I can write a query that says give me back post ID or give me back ID 1, and then I get back my post as one record,
Yeah.
and then all my comments.
Mhm.
And then I can deserialize that by just looking at the entity type and saying, oh, that's a type post. So I'll deserialize that into my my POCO type or post class. And then I'll take that array of all those comments and I'll deserialize that into an array of my comment class.
Right.
So that's modeling in that sense. Then the other last piece of that is partitioning. So we're horizontally partitioned. What this means is that every different value for that partition key could be stored in a different computer. We have physical partitions within Cosmos. We try to make people think about logical partitions, so each of the different values. Each logical partition has a size of 10 gigabytes, right? And that's roughly kind of the compute storage boundary for what you can store in there. So this is another really key aspect that you don't think about in a SQL database, is you have to think about where partition is my data stored, and then when I operate on it, I have to do it within that partition. An analog to this is if I tell a friend of mine to come over, I tell him what block I'm on, and on my block I've got 4 apartment buildings, and I say I'm on this block and I'm in unit 202, and I don't tell him anything else. Like I don't tell him what building I'm in. He has to go to building 1, go up to flights of stairs, knock on 202, and see if that's me. And if that's not me, then he has to go back downstairs, go into the second building, go up 2 flights of stairs, knock on that door, and see if that's me. And then 3, and then 4. This is basically a cross-partition query. So he had to go into 4 different buildings or 4 different partitions, and then use the index to go find room 202, and then see if it was me. Versus an in-partition query would say, Mark is in building 4 in unit 202, right? So the partition is the building, the unit number is the index, right? That's how you think about data in a partitioned data store, is you have to include the partition key as part of the query because it tells the engine what partition your data is in. And that's how you get super high efficiency. The nice thing about horizontally partitioned data stores is that it works just as fast on a megabyte of data or a petabyte of data. That's not true in a relational world. In fact, you can't put a petabyte of data on a SQL server. It just doesn't work. Well, maybe on hyperscale.
Yeah,
But they're using partitioning to do it. So it's essentially using what we've done is to horizontally partition the data. So yeah, maybe when I come back, I'll do a whole session on just partitioning and modeling. It's absolutely critical. In fact, anybody that comes from a relational background, go learn about modeling and partitioning for Cosmos before you do anything. Because if you try to use Cosmos like a SQL server and put different entities in different containers, you're not going to get good performance out of it.
Right, and for the room the point of view, we have a great video about the partitioning. There are several, and including conductivity. So if you are interested in Cosmos DB, the first thing you recommend is go to the overview, like this one, then modeling, partitioning, and then only then we can decide the consistency or availability, right?
Well, I would say go look at the stuff I talked about because it's fun.
Right.
And it's distributed systems, right? So that's fun to play with.
Yeah.
But definitely go, and I tried to see if I could. Whoa, okay, this is a Japanese keyboard. I just realized. That's probably not going to resolve. Yeah. Azure. If I send anybody anywhere, I want to send you to this page to learn about modeling. Well, go here to learn about partitioning. And then, where is it? Oh, sorry. Keep scrolling because we have lots of docs. That's not it. Where do they move this stuff? Sorry, moving our docs. Hold on. Huh. That's not it. Modeling. There it is.
Yeah, there you go.
So start here. How to model and partition data. So this will walk you through an example. It takes the blogging platform sample. So it starts with a blogging platform where you have a table of users, a table of posts, and a table of comments, and then shows you how to migrate that into a properly partitioned model for a NoSQL store. If you want to migrate, you can migrate pretty much any relational model into this type of model. Depending on the complexity of what you're doing, it will tell you how hard it's going to be. But there's really nothing you can't put into a NoSQL store. It's just a different way of thinking about how do you store data. There's also other tricks in here too. Like we have a feature called change feed right here. Change feed, what it is essentially a pub sub on top of Cosmos. So if I write any data into any container, I can take it and react to that and then push it into another container. So let's say I've got a container, like let's say if I have to maintain a relationship between two different entities in a relational world, I would have that one-to-many relationship and then use the referential integrity between those two things and then put up constraints to make sure I never break that. In a NoSQL world, that type of stuff just doesn't exist. But you can still enforce that type of thing by using change feeds. So let's say I go and I have a customer and his ID is Mark Brown. And then I go and change my name so my ID is now John Brown. I could go and do an upsert into my collection of customers or people, and then I would use change feed to say, oh, Mark Brown changed his ID to John Brown. I'm going to run my Azure function that's then going to upsert another container where I have all of those Mark Browns and make them all John Browns. So that you can use change feed to basically use that to maintain referential integrity between those types of things. You could also use a graph actually as well. Graph is a great way to represent relationships between data using NoSQL as a backstore. So anyway, this is another killer thing. So learn modeling, learn partitioning, learn change feed, because change feed is like the magic that makes a lot of things really, really easy and possible. And it integrates well into functions too. So good segue there back to our previous talk. Okay, has everybody had enough? I'll just keep talking, dude, if you don't stop me. So 9:30.
Yeah, well, usually I stop, but because this is a very rare opportunity for us to having the two product team members, I didn't bother really.
Oh,
And it's holiday today.
Yeah, I know. You got new emperor today, right?
Yeah.
Congratulations, everyone. One time.
Banzai kind of stuff. Yeah. So I really didn't want to stop. Even Katy, I really didn't want to stop her from the talking the detail. But as we all know, if we speak about the very detail of the one product, we need kind of 1 week to complete all the session. But this is great, and I really appreciate your time to. Sure. Actually, he made an effort to coming back to the office several times to find out where I am. It's my bad though. I really appreciate it. All right, so that's everything for today. And obviously, I do not want to use more time to wasting your time. So for the .NET Conf stuff, even though there's a bunch of the video, like 77 video, there's a way to categorize where you are interested in. Like if you're interested in new feature like C#8 or .NET Core 3, or if you're interested in more like the client side, IoT or machine learning or the Blazor, or if you're interested in more like the server side with a container like the Kubernetes, kind of stuff. You can try to find out the category where you want to look into, and there is up to 10 to 12 video for that category. So I really encourage you to start watching the video, because the good thing about the video is it doesn't have like 1 hour video. Usually 40 minutes, 35 minutes, so it's easier to watch for Japanese commuting time. So I hope you enjoy that. All right, so thank you for coming today, and next month, I do not set the date yet, but I try to set up the next one as well. And I also want to hear your opinion about your request about which kind of technology you want to listen to. But the reason why Cosmos TV is very important is this is another new wave of the cloud native, the development style, and .NET Core is very, very optimized for the cloud native anyway. So this is very important to understand as a .NET developer. All right, so thank you for coming, and if you're not writing down your name yet, please come in front to write down your name. And let me just pause the YouTube here, and thank the people watching the YouTube. See you later. So coming back, and